So a Bayesian model has two components to it. To define a Bayesian model, you have to define the prior and the likelihood plus prior equal a Bayes model. And all their inference and learning happens through the Bayes equation. So let's say you have parameter theta that you're trying to learn and you want to calculate posterior given some data set X, and it's just a product of the likelihood and the prior divided by the total probability or the evidence. And as I mentioned in the previous video, usually this one is hard to calculate because the calculation of the total likelihood or total probability, you need to integrate out the parameter theta from the joint distribution. So it's p of x given theta, p of theta, and you have to integrate theta out, and you integrate over the domain of theta, and this integral is hard to calculate. And in most of the cases, this integral cannot be calculated analytically. However, there are exceptions. If you, for specific combinations of likelihood and prior, this integral is actually can be calculated. For specific likelihood and prior pairs, we can analytically calculate this integral. Which means, so from this, the statement that we can make is that the posterior is actually analytically calculatable, can analytically calculate posterior. So, and if you give me a likelihood, and there happens to be a prior for this likelihood that leads to that situation when the everything can be analytically calculated, this prior is called conjugate. And what happens is, so in this situation we have a conjugate prior. And the reason it's called conjugate is because the posterior will be from the same family as the prior itself. So if prior is normal and it's conjugate prior, meaning that posterior is going to be normal as well. So we'll see examples. So prior and posterior will be from the same family. So let's do a formal definition. So let's say we have F that denotes a class of distributions. And we have class pi of prior distribution, and we'll say that pi is conjugate for F if the posterior distribution is in the class pi for any distribution from F. Okay, so we say F, we say pi conjugate to F if the posterior, so we say prior pi conjugate to likelihood F, if posterior from the same family as pi, family of distributions as pi itself, as the prior. Okay, so here's a quick example. Binomial beta. Let's say you have a data set and your data set follows Bernoulli distribution. So it's just a coin flip, and Bernoulli distribution parameterized by this parameter P, which is the probability of success of each of those Bernoulli trials. And you can define a prior on this parameter P to be a beta distribution. Beta distribution has two parameters, alpha and beta. And remember, the beta distribution is defined so that the main for beta distribution is 0, 1, and beta distribution. So that's beta distribution, and alpha and beta basically control the shape of the density function curve. And so it's rather flexible. You actually can model something which is close to uniform prior on 0, 1 using beta distribution. Gives you a lot of flexibility. And so the question is, how do we choose the values of the hyperparameters? So in this case, parameters of the prior distribution, alpha and beta, they're called hyperparameters. So alpha and beta hyperparameters. And you can use the property of the beta distribution to help you in deciding about alpha and beta. So one of the properties is that the mean is the ratio of alpha and alpha plus beta. So if you choose alpha equals to beta, then your mean is going to be 1/2. So for example, that your most likely value for the p is 1/2, then you should be choosing alpha and beta equals to each other. And a couple more things to keep in mind. So one thing is the mode of distribution. Mode is given by alpha minus 1 divided by alpha plus beta plus 2. Again, so if alpha and beta are equal to each other, you have alpha minus 1 to alpha plus 2. So you have 1/2 in the case when alpha and beta equal to each other. And the variance is a little bit more complicated form, but variance is given by, so the variance of beta distribution is alpha beta on the top, and on the bottom you have alpha plus beta squared multiplied by alpha plus beta plus 1. Now, well, actually, let's look at the beta distribution so you get a little bit more intuition behind how it works. So let me switch the screen. So that's the density of the beta distribution for alpha and beta equals to 1. And if I change alpha and beta equal to 5, for example, so I'll get something that, again, has a mode at 1/2 and expected value is 1/2, the average, but it becomes just a little bit more focused on 1/2. And if I increase my alpha and beta values, so if I change them to 20, you'll see them getting more concentrated. Basically, the variance will go down as my values go up. And again, if I don't want things to be centered at 1/2, I basically can take, for example, alpha 10 and beta 20. So my average is going to be 10 divided by 30. It's 1/3 in this case, and I can keep changing my parameters to get the shape that I would like of the distribution. So here I'm looking at the parameters between 1 and 20, and you can get bimodal distribution when you're outside of this range, when alpha or beta is less than 1. But so far we're looking at this unimode case, which is the most common one. Okay, so let's look at the beta binomial example. So one thing to keep in mind is how to find a conjugate prior. So for example, you always start with likelihood. You always start with assumption about the distribution of a data, and let's say assume that your data follows binomial distribution. So let's say you know that your likelihood is binomial, means the probability for each of the samples is going to be, a likelihood function is going to be theta raised to the power y times 1 minus theta raised to the power 1 minus y. Okay, so that's your likelihood in this case for the binomial distribution. And then if you want to think of a conjugate prior, you have to ask yourself, okay, is there another density function that has a very similar functional form? And in this case, it happens to be beta. You remember that the PDF for beta is well, I'm gonna use theta now. Theta alpha minus 1, 1 minus theta beta minus 1 divided by the beta function of alpha. So it's just a constant here. So you basically have a similar looking function. And essentially, this is a shortcut for how you can think of a conjugate prior for a given likelihood. So let's write down it fully. Let's say you have this likelihood. You have T, capital T observations, and so the likelihood is just the product of the binomial density functions. So you can simplify it into a single expression. And if you start with a initial prior distribution of theta to be beta, and here I'm using small a and capital A instead of alpha and beta, then you actually can calculate posterior analytically in this case. So the density function of the prior is given as just density of the beta function, and then the posterior actually can be calculated analytically. So the posterior distribution over theta given y also will follow beta distribution, so it's from the same family as the prior. And the parameters, again, we can calculate analytically. So the update for the alpha parameter, for the first parameter, which is basically called the shape parameter, is the a, which comes from the prior hyperparameter, plus the sum across all of the y's. And the update for the second parameter, the capital A, is also you take the hyperparameter from the prior, and then it's t, the total number of observations, minus, again, the sum across all them. So if you think just intuitively about this, so let's think about the case when half of your y's are zeros and half of your y's are ones. So in this case, so simple case, case 1/2 of y's are ones. So in this case, then this sum over yt is just going to be t over 2, okay? And so a new value of a is going to be a plus, sorry, it's not t over 2, of course. It is, yes, it is t over 2 times plus t over 2. And your new value for capital A is, again, a all parameter plus t minus half t, which is t over 2. And so let's say you started with a small and capital A to be equal to 1. Then in this case, your at will be 1 plus t over 2. And the new parameter at is going to be 1 plus t over 2. So you started with a and capital A to be equal to 1. So you started with a flat prior from 0 to 1. So your prior was like this, from 0 to 1. And your posterior, remember, the larger values of the parameters of beta distribution, the more peakier our distribution at the center. So again, both parameters will be equal. So the posterior will have a shape like this. It's going to peak at 1/2. Okay. And the larger the value t, the less of a variance going to be of your posterior. So intuitively, it makes perfect sense. How do you do those calculations? How do you calculate the values of the posterior distribution? So you just have this product of two functions on the right hand side. So one is the likelihood function with just product across your individual density functions. And then you have the density of the beta function. So that's your prior here. And we use this sign, which stands for proportional to. proportional to, meaning it's proportional up to some constant. Instead of writing the full density on the right hand side, we just skip constants, means we just skip constants. Okay, so if we skip the constants, we have this density that is proportional to the posterior density on the right hand side. And now it just becomes an exercise of correctly calculating the powers of P. So you basically have to sum up these, and then you have to sum up these and these. And when you do those things together, you get the final result that alpha parameter update is just the sum across all the y's. And the beta parameter update is n minus sum across all of the y's. And another way to think about this is that beta, the posterior mean is just a shrinkage estimator. If you calculate the expected value of the p-value after the data was incorporated into your distribution, meaning the p-value from the posterior mean, so it becomes alpha plus the sum across the y's divided by alpha plus beta plus n. And you can simplify it or rewrite this expression. So you can take y bar, the average across y's outside. And so you have some parameter a times y bar. And then you have this b plus your previous p, the p bar, so that's p bar from prior. Okay, and what you can see is that the expected value of the posterior distribution of p is just a combination of the weighted sum of the p-value from the prior and the value y hat, which is the average across all of the observations of y. So you're basically averaging out data and value of p from your prior distribution. So here's a quick example of beta binomial. There was a book by Taleb called The Black Swan, and he was talking about this highly unlikely events that happens once in a while, and those type of events that a human might not experience in one or two generations, but maybe happens every other generation. So you haven't seen it for a while, and you grew up not seeing something like that happening, and then something like that actually happens. So the fact that you have never experienced or never seen something doesn't mean that it will never happen. And essentially, to study those type of phenomena, you can just use this beta binomial model. So suppose that you have t trials, and you only have seen successful outcomes. So all of your previous observations about this variable y equal to 1. And the probability of the next trial being successful outcome according to this beta binomial model is just t plus 2 divided by t plus 1. So it, again, so we assume that the prior parameters are 1 and 1 here. So we assume this flat prior to begin with. So a quick example of, and this is one of the differences between the Bayesian approach and the frequentist approach. So a frequentist would calculate the y bar, which is just 1, and then estimate for p, the frequentist estimate for p hat is going to be just equal to y bar equal to 1. So the frequentist estimation will say, yes, if we've observed only once so far, then if we want to predict what's going to happen tomorrow, we're going to predict with probability 1 that next observation of y is going to be 1 as well. So let's say you see the sunrises, and you saw 1,000 sunrises so far, and you try to predict whether the sun will rise tomorrow or not. So the frequentist said, yeah, the sun will rise tomorrow for sure, and the Bayesians say, no, actually, there is a probability that the sun will rise is 1,000 plus 1 divided by 1,000 plus 2. So it's number very close to 1, but not exactly 1. So you always leave this chance of a black swan in the Bayesian learning, and essentially Taleb through this book argues that this is the right approach to do things, you always have to assume that something can happen even though you've never experienced something of that sort. And so here are the calculation. The probability of never seeing a black swan goes to 0 as number of observation goes up. But eventually it happened, and you basically don't have to be surprised if it actually happens.